Unit 4, we talk about transportation, assignment, and network models. In addition to that, we also talk about decision analysis. And so what we'll be covering in this particular session is the transportation, assignment, and networking part of it. Okay? So our objectives are as follows. So we want to structure special linear programming network flow models. So basically, we want to study what are some of the basic things that we talk about in a network model. So such things such as, what do we call a supply node? What do we call a demand or destination node? And how do we interpret that? We'll also talk about what a transshipment node is and how we interpret that as well. We'll also see several examples of how to set up and solve transportation models. And we'll set up and solve transportation models with min, max, or max, min objectives. And we will also talk about transshipment models as well, where we're having to ship product to a central location for processing or inspection or something like that. And then from the transshipment location, ship to the destination location to get it to our end customer. And so we'll see some examples like that as well. So we'll also look at setting up and solving some maximal flow network models using our Excel solver. And we will set up and solve some shortest path network models using the Excel solver. And then finally, we'll talk about connecting all points of a network while minimizing the total distance using what's called a minimum spanning tree model. And it sounds more fancy than what it is, but we need to kind of get going here so we can see what a basic network model is. And from that, you'll kind of see how all this comes together. So when we do network flow models, a lot of this comes from graph theory or networking theory. And networking theory or graph theory is just a basic way to take a situation and say, how is everything connected, but look at it in an abstract way. So that's essentially what we're doing here. But since we're trying to model business situations, of course, there are going to be some equations and or inequalities that sort of result from that. And thus, that's why we'll need to use the Excel solver and linear programming techniques. All right, so when we talk about a basic network, we have what's called arcs and nodes. And so arcs are the lines or the arrows or the edges that you see there, and the nodes are the circles or the points that you see that are numbered. So we have three types of nodes. We have supply nodes, demand nodes, and transshipment nodes. So we need to look into each of these to sort of figure out how we interpret it, how we label it. So we see here that for decision variables, they represent flows. And so whenever we talk about a supply node, demand node, or whatever, one of the things that we're looking for is the net flow, meaning how much of whatever it is that we're modeling goes into a node versus what goes out of a node. And so the difference in between what goes into a node and out of a node is called the net flow. And whenever we model these, we're using basic whole number coefficients, or I should say integer coefficients. And usually we're talking about zeros and ones, but of course, if we're talking about supply and demand, we're going to be also introducing some negative numbers here. And so most often, we'll either use -1, 0, or 1, or if we are trying to quantify something like distance or the cost of something, then of course we'll use those particular numbers. So to start us off, we are going to have this transportation model. And just to set this up, we have a furniture company, and they're trying to ship some product. And of course, we need to produce the product, and so they'll be produced in the factory places. And if you see here, we have a factory in Fort Lauderdale, we have one in Evansville, and we also have one in Des Moines, Iowa. Evansville, Indiana, and Des Moines, Iowa. And from there, what we want to do is ship to our end customers in Albuquerque, in Cleveland, and in Boston. So that's the idea. And so what we want to do, of course, is find the cheapest way to be able to do that, because we want to cut down costs so we can increase our profits by doing it. So that's the basics or the basis of this particular problem. Now, here's the information that's given to us. So we know that from in Des Moines, we're having 100 units being produced. And so this could be, tables and chairs again. Evansville, we have 300 units being produced there, and in Fort Lauderdale, also 300 units. And so we have a total of 700 units that we plan on shipping out to our destination places, which is our warehouses in Albuquerque, Boston, and Cleveland. And so if you can look at the shipping routes, you'll see that for Des Moines, Evansville, and Fort Lauderdale, every factory has a way to ship to every destination. And so in graph theory, what we call this is a complete graph, where every node, as we want to call it here, is connected to every other node. And so we're basically saying that, hey, any of these factories have the capability to ship into any of our destinations. And we see that the demand from our destinations are 300 for Albuquerque, 200 for Boston, and 200 for Cleveland. And of course, that totals out to be 700 units as well. So in this case, the total amount of units that we're producing within a production cycle, all of that is being demanded or used up by the destination locations. So what that's going to turn out to be is that whenever we model this situation, we are going to have equations that we're dealing with. Okay? And so please keep that in mind. Whenever supply equals demand, we have nothing but equations in our model. Whenever we have supply is greater than demand, or demand is greater than supply, then we tend to have inequalities in our linear programming model. So I just want to make sure that we are aware of that before we get deep into this. Now, here are our transportation costs. And so we see that if we're shipping from the factories into the end destinations, to ship from Des Moines to Albuquerque is $5, for example. But to ship from Evansville to Albuquerque is $8. So you can look there and see that we have all these different prices based upon where it's coming from and where it's being shipped to. And again, our goal in this case, we're actually talking about shipping desk from the factories to the destination locations to our end customer. So we want to determine the number of desks to ship on each factory to warehouse route while minimizing the total transportation costs. So again, our goal here is to get as much product out, or in this case, all 700 units from factory to destination location by spending the least amount of money as possible. All right, so before we start to actually model this mathematically, what we want to do is label what our decision variables are going to be. And so what our decision variables are going to be are the number of desks going from one location to another. And so the way that we're going to label that in this example is X, and then in subscripts, we're going to put IJ, where I is going to stand for the factory that that the desks are coming from, and J is going to represent the warehouse or the end destination that the desks are going to. So, for example, here, let me make sure that this is writing correctly here. So let's say if I said X sub FC, then what that means is that I'm talking about the number of desks that I'm shipping from Fort Lauderdale to Cleveland. Okay. And if I said X sub EB, then that's saying the number of desks I'm shipping from Evansville to Boston. So that's how we will label these. When we model this, of course, if you notice, all of this is our objective function, but where it comes from is all of the cost that we were quoted earlier. So let me go back there. So here, we know that we're trying to keep the total cost down here. And so how this objective function is formed is, if you notice, you're coming from Des Moines to Albuquerque here. So here, this is $5 times the number of product that you ship from Des Moines to Albuquerque. Of course, this is from Des Moines to Boston, from Des Moines to Cleveland. The next is from Evansville to Albuquerque, from Evansville to Boston, and from Evansville to Cleveland. And then lastly would be from Fort Lauderdale to Albuquerque, Fort Lauderdale to Boston, and Fort Lauderdale to Cleveland. And of course, you just add all these up. And when you add these up, what you're getting is your total cost, and your goal is to minimize that. So that's where this particular objective function comes from. All right, so now what we need to do is model our supply and demand. And so one of the things that we need to pay attention to here is that whenever we talk about supply, we're talking about product leaving a node. So what we're actually saying here is, and I'll go back to, let me go back to here. So here, we want the net flow going from factory to destination to be 0. So let's say, for instance, here, we're talking about the 100 units. Whenever we talk about things in terms of what we call pure supply nodes, what's going to leave out is going to be negative. When we talk about a pure demand node, we're going to say that's positive. So, of course, pure supply means what's leaving. So anytime you see something that's a pure supply node, you'll model as being negative. And anytime you see something that's pure demand, it's going to be positive, meaning what they receive. So negative means leaving the node, positive means coming into the node or receiving the node. Okay? So when we look at it that way, you'll see why the Des Moines supply, which is the number of desks going from Des Moines to all 3 of the destination locations, Albuquerque, Boston, and Cleveland, are equal to -100. And of course, the negative is just identifying that that supply is leaving that particular node or leaving the factory. So similarly, we know the same thing for Evansville and Fort Lauderdale. And so now, with the demand, we know that the demand is going to be what is received by the destination locations. So of course, we know for Albuquerque, we got stuff coming from Des Moines, desks coming from Evansville, and desks coming from Fort Lauderdale. They're all coming to Albuquerque. And we know that that was 300. Boston and Cleveland, we knew that we had 200 for the amount of demand of desks there as well. Okay? So just coming back here for Des Moines, if we just follow one of these edges here, this is the supply. So we're saying that what's leaving Des Moines is going to be negative d sub A, and then here, negative, this is going to be d sub B, and then here, that's negative d sub C. So going here, here, and there. And of course, when we talk about everything that's being received from Albuquerque, then of course, we notice here that this is going to be coming from Des Moines to Albuquerque. And from here is going to be coming from Evansville to Albuquerque. And we notice from here, it's going to be from Fort Lauderdale to Albuquerque. What's the same there is Albuquerque. And we see that we have a total of 300 units. So that is how, in this case, we would be modeling the supply and demand for Des Moines and Albuquerque. And of course, we can do the same thing for all of us. So now that we see how to set that up, then of course, this is how we could do it in Excel. And so here you see that for the demand, for the supply, everywhere where we got something leaving out of the Des Moines factory, we put negative ones there. So if you remember, we had negative x of dA minus x of dB minus x of dC equals, I believe it was 300, okay? And so, oh, sorry, that was negative 100. So here, we just have negative 1 times the x of dA, negative 1 times the x of dB, negative 1 times the x of dC, and of course, we're wanting that to equal 100. And here, all we're doing is keeping track of exactly how much supply actually came out. And since supply equals demand, of course, we want all that to be used up. So of course, same kind of thing with the Evansville supply. Got everything per Evansville here, and then everything per Fort Lauderdale. And of course, the negative number, the negative ones just represent supply, and the positive ones represent demand. And for those of you that are in my course, of course, you can download the Excel files for Unit 4, which is, in this case, Chapter 5. And you can see this example in all of the equations that are coded in, for instance, for the objective function, and to keep track of how much demand is actually used up. Okay. Then, of course, you want to go here to your Excel solver. Make sure that you have your objective function in by changing all of the cells that are in yellow. And then, of course, your constraints will be all of these equations here. And this is just another alternative way of tracking this or modeling this. You could sort of pick what you like, but at the end of the day, it still ends up being the same thing as what we've seen here. And I'll go ahead and get rid of all of this, because we'll probably need to come back here later. All right, so of course that's what this would look like if you modeled it this way. Again, same equations, just if you want to look at it differently, you can. All right, so now we've talked about a situation where we have supply meets demand. So now let's talk about a case where supply exceeds demand. Okay? So in this example, we know that our total supply is going to be 750 desks, but we're only being demanded to get 700 desks to our end destinations. So because of that, our supply equations are now going to turn into inequalities. And so they're doing that only because we have more supply than demand. So we can give that amount or less. Now, one thing I do want to clear up here is that since we're using the, whenever we have supply, we're referring to that as negative, and whenever we have demand, we're referring to that as positive. The way that we have to do our inequalities here is slightly different. And I just want to use this first one as an example to kind of iterate what I'm talking about. So here we know that if we have a supply of 750, that means we can supply 750 desks or less. However, we see our inequality here is greater. But one of the things that we have to remember about inequalities is that anytime we multiply or divide by a negative number, we have to flip, or more properly said, change the sense of the sign. So here's my point. We know that if we were looking at this normally, we know that the number of desks coming from Des Moines to Albuquerque, plus the number of desks coming from Des Moines to Boston, plus the number of desks coming from Des Moines to Cleveland, would be 750 or less. And that is expressed as less than or equal to 750. Now, if we multiply both sides of this equation, inequality, by -1, then you're going to notice that all of our terms end up being negative instead of positive net. But what also happens is, since we're multiplying by a -1, we have to flip the sign. And so that's why you see everything written in terms of greater than when it's negative. Okay? So I wanted to make sure that we got that cleared up. So even though it says this all in negative, if you wanted to, you could really just write it as this is less than 750, and that would be equivalent to it. But again, we use the negative to help us to be mindful of what we're talking about when we talk about pure supply versus what we're talking about when we talk about pure demand. So in the case where supply is less than demand, or put another way, demand is more than supply, then our demand equations now turn into inequalities. And so, of course, in looking at it this way, we see that the demand is going to be greater than supply. So we have this. You know, our old demand was 300. New demand has risen some for Albuquerque. So now we have a situation where we have less than. So we're saying everything that goes in Albuquerque can be 350 or less. And of course, that will still be less than, but again, we don't want to supply more than 350, but we know that the demand is up to 350. Okay. All right, so that's how we deal with situations where when we have supply is more than demand, or demand is more than supply. We also use what's called dummy nodes in transportation models as well. So we'll dig into this and try to give you an idea of how this is used. All right, so for min, max, and max, min objectives, when we do max min, we want to maximize the minimum value of a decision variable. And when we want to do a min-max, we want to minimize the maximum value of a decision variable. And in our example here, what we want to do is minimize the maximum amount shipped on any specific route. So that's the example that we're going to use here to kind of explain what's going on. Again, if we want to change this example a bit, we want to minimize, in other words, make it small as possible, the maximum amount shipped on any specific route. And so what we're basically trying to do is even out our risk by getting as close to, or if not the same amount, shipped out of each particular plant to the destination places as much as possible. Okay? We like to keep the flow of desk pretty even across the board if we could. All right, so if we do this example here, the min-max example, then our goal here is to minimize the max quantity shipped on any route. So again, if we take the situation where we have supply is equaling demand, our supply and demand equations pretty much stay the same as they were in the beginning. Okay? But now we see what's different is we want to minimize the max quantity shipped on any route. And so to do that, one of the things that we're realistically going to have to do is allow our minimum cost to be increased some. So let me go back a few slides to kind of show you where all this comes from. And I'll come back here. So when we originally did this, we modeled a situation where we had 700 total desks had to come out of all our factories, and it had to go into all of our warehouses so that it can get to our end customer. Okay? And we saw that with that particular model of supply equaling demand, we had total shipment cost to get those desks to all those locations of $3,900. Okay? Now, this is the optimum solution based upon what we model. If we want to change these numbers here, or in other words, change the amount that we deliver from a factory to a destination warehouse, then we're going to have some flexibility in our budget as far as how much we're able to spend to get those particular products there. Okay? Now, another reason that we want to do this is because, and I'll erase what I'm circled here right quick. If you notice, we have some situations where we don't have anything going on these particular routes here. Okay? So if you see from Des Moines to Boston, we don't have any desks coming from the Des Moines factory to Boston. Okay? We don't have any coming from Des Moines to Cleveland. So all the product that we have from Des Moines is going directly to Albuquerque. Okay? And of course that makes sense because geographically speaking, Des Moines and Albuquerque are closest together. Okay? Now, if you also see here that for Fort Lauderdale going to Boston, the Fort Lauderdale plant has nothing going to Boston. Okay? The issue with this is that what if we have a situation where there's something going on with the Des Moines plant, like let's say it's a big snowstorm or something like that, and they can't get those desks out. So that means for Albuquerque, if you know the Albuquerque demand is 300, we're not going to be able to meet that demand if something happens at the Des Moines, Iowa plant or factory. Okay? And so we're going to be short by 100 desks, which is going to be a problem. Okay? And so to be able to sort of smooth everything out and say, all right, well, we may not be able to supply all the demand, but let's be able to supply enough of it as possible by spreading out how many deaths actually come from each factory. We want to make it as even as possible. And so to do that, what we have to give up is spending the least amount of money as possible. And so when you really look at it, it'll make sense, because what do you stand to lose if something happens to your Des Moines, Iowa plant, and you can't deliver this 100 units? Then what you just did was decreased your revenues by 33%. Because remember, you have 300 deaths that you need to be able to deliver, but you're only able to deliver 200 of the 300. Okay, so that's a third. Now, what you're selling those deaths for is probably going to be a lot more than what the increase in your travel budget or your shipment budget is going to be. So in a way, what you're doing by increasing the budget is sort of putting in some insurance for yourself to make sure that you get the most amount of product to all of your customers as possible. Okay? So in this situation, that's why we're increasing the budget by 5% from $3,900 to $4,095. And of course, now our objective function was an equation before, but now is going to be an inequality. Okay, so this is an extra added constraint that we have. Our objective function is still all of this, but in addition to having that, we have an extra constraint that says that what we spend on this has to be $4,095 or less. Okay? So that's what we mean by minimizing the maximum amount of deaths that can be delivered. So to do that, we have to be flexible on shipping price. Now, we also have to make sure that we pay attention to this. And so what this is saying here is that all of our variables, of course, have to be non-negative, but this is saying that the amount that we're shipping from Des Moines to Albuquerque is going to have to be less than or equal to this particular number. Now, it's written as S is greater than or equal to X sub dA, but if we turn that around, like how we read in this hemisphere, it looks like this. And so this is the maximizing part. Okay? So here, we're saying the number of product that goes from Des Moines to Albuquerque has to be less than or equal to this particular amount that we're trying to figure out. Okay? So all the demand that we have, or all the number of deaths that are going to be shipped, are either going to be this number or less. So that's what we're trying to do, balance that. All right, so if we set that up, then of course price structure stays the same, and the flow balance equations as far as what the supply is and what your demand is, that stays the same. Okay. Now, the other constraints that we have, notice that we're now keeping track of the total cost, and the total cost has to be less than or equal to $4,095. So that's where the extra constraint comes in there. We also are making sure that whatever amount that we have going from all these locations here are going to be less than or equal to whatever that value S is. Okay, or put another way, S is greater than or equal to whatever that value is. Okay? And so this is your left-hand side, which is what S is. this is your right-hand side here, which is what you're actually tracking. Okay? And so if you notice, all these values here are values that are less than the 102.5. Okay? And so you're saying, theoretically speaking here, if we could ship 102.5 from all factories and make it go to all destination locations, then we would be minimizing the maximum amount that we can ship to all those places. And thus, we're spreading out our risk just in case something happens to one of our factories. And again, when we set this up, of course, if you notice here, you're going to minimize cell B16. And B16 is this cell right here, which is the max min flow. Okay. All right, so let's move on. So one other thing I wanted to show you. Trying to make sure I'm trying to find it here. All right, yeah, so that was it. So here, how we actually come up with this number here is, again, remember, we're trying to make sure that whatever we come out with here is the same thing that is there. So we're trying to minimize that amount, but at the same time, maximize the amount that we can send. Okay. And of course, these are all of our constraints down here, which is basically your flow balance equations. Sorry, not your flow balance equations. So let me get rid of some of this. Yeah, so here, your constraints that we have, these are going to be all of these equations there, right, and inequalities as well. So for this first one here, you have H14 is less than or equal to J14. So this is H14 here. This is J14. And that's on its own. This next one here is an array from H15 to H23. And so that's everything from here, H all the way down to here. And of course, that's the right-hand side. So that first one just takes care of making sure that you have some flexibility on your spending budget for transportation and transportation and shipping. And the other ones here are trying to make sure that whatever this value ends up being, all of these values are less than. Okay. All right, so at this point, we've seen how to look at a transportation model where we have supply equals demand, where supply is greater than demand, where demand is greater than supply, and also in a situation where we need to minimize maximum amount shipped to any location. And so we've seen how to deal with all that. So now next what we need to deal with is what we call transshipment models, which means we have our factories shipping to a central location or central locations to do something like inspect or do the second part of developing the product, and then after that we ship the resulting product to the end customer. And one of the things that we know here is that for transshipment modes, the net flow going in and out should be 0. So that means everything that goes in must go out. So that's why here it says transshipment nodes should be 0 on the right-hand side of your equation or inequality. And so with transshipment nodes, it should be just an equation. So for demand, of course, depending on whether we have more supply than demand, or if it's equal, you may have an equation or an inequality. And remember, a pure supply node, negative, meaning that the product is leaving. Pure demand node means that the product is being received. So that's why it's positive. Of course, transshipment node, everything that goes in is also going out. All right, so if we revise our current situation that we have, let's say we have a subcontractor that's willing to deliver these desks to all of our locations by giving us competitive pricing, to deliver each desk. So we see here that we have a contractor in Evansville, and their prices are so cheap relative to whatever current deal we've had. We're considering we need to ship all of our product to Evansville, no matter where it comes from. We need to ship it all to Evansville, and then from Evansville, ship it out to our destination warehouses so that we can get it to our end customer. And so if you notice here, the $3, the $2, $1 is way less than what it is coming from Des Moines or Fort Lauderdale. Okay. Now, notice that because of that, we've actually had to add another column. And this other column basically says, all right, we now need to figure out how we're going to ship everything from Des Moines and Fort Lauderdale to Evansville as well. And so we have some new decision variables that we have to account for. Okay. Now, of course, the only place where you won't see that is here, because we can't ship to ourselves. I mean, we could, but it's not going to really help us. Because remember, we're still making product in Evansville as well. And so that product is already there. So there's no need to model costs from going from Evansville to Evansville. Doesn't make sense. All right, so now what we want to see is what actually changed. Okay, so this model stays the same, but now you see how all the desks that are being made in Des Moines, Iowa, we now want to ship to Evansville. And we also see what's made in Fort Lauderdale is also being shipped to Evansville. So in addition to everything else that we had, this is what we had. And you see that we still have what is going from Des Moines to Albuquerque, Des Moines to Boston, Des Moines to Cleveland. But we also have Des Moines to Evansville. And of course, for the supply nodes, of course, now since we're actually going to ship all of our product to Evansville, we need to be able to know what came from Des Moines to Evansville as well. So we got to track that. Now, for the Evansville supply, of course, we know that we have product coming in from Des Moines to Evansville, and we have product coming in from Fort Lauderdale to Evansville as well. So now that we're using Evansville as a transshipment node, we have to account for the product that's coming from Des Moines and Fort Lauderdale, in addition to what's going to be coming out of Evansville itself. Okay. So this is all the product that's going to be made in Des Moines and Fort Lauderdale, and here, and here is still what we are making in Evansville, but shipping out to all the 3 destination places. Okay. And so then for the Fort Lauderdale, of course, we have to take into account what we're actually shipping to Evansville. since, again, we got a contract there where shipping prices are so cheap that it's probably advantageous for us to ship everything out of Evansville to make it happen. So now with those new things added in there, with this new contract, you see that we slash our cost by $1,300. Okay, and if we're doing shipments like this, let's say every week or every month, you can see how that adds up to really saving us some money. Okay. Now, you also see that whenever we run our Excel solver here, what our solutions look like. So we see that for Des Moines, we still have some product going from Des Moines to Cleveland. But we see for the most part, Evansville has 300 going to Albuquerque. Evansville has 200 going to Boston. Evansville has 100 going to Cleveland. And of course, for Fort Lauderdale, it seems like, of course, all that product is going to Evansville. Okay? So the point that I want to make here is that even though we have cheaper pricing and we want to ship everything to Evansville, if you notice, what's happening here is that we still have some product, mainly the Des Moines going to Cleveland. It's still better for us to actually have those units go directly from Des Moines to Cleveland, even though we know we got cheaper pricing in Evansville. And so by us setting this model up and letting the Excel solver do the work for us, we kind of see how many units and from where actually need to be shipped to Evansville to get this attractive discount in shipment price. Okay. All right, so let's go ahead and move on. So now what we want to do is look at this a little different. So now we have another situation where we're going to use the transshipment model. And Lopez Custom Outfits is basically a high-end costume making company. And they make costumes like togas and other stuff like maybe Halloween or even Mardi Gras for high-end customers. So they make these basic costumes, or the base for all of them, regardless of what you have. They make them in Albany and Boston and Hartford. And so what they do is they have a specializing and inspection location in Charlotte and Richmond. And so that's going to be your transshipment nodes in this particular model. And then from there, from Charlotte and Richmond, they ship to their end customers in Dallas, in Louisville, in Memphis, and in Nashville. And so what we see are the shipping costs for all of those. So this is, of course, the shipping cost once the basics of the product is made to get it to the specializing or the finishing, as they call it. Okay. And finishing just means if I want some special rhinestones on there or something like that, I will put that on along with inspecting it to make sure that everything is how it's supposed to be. There's no holes. There isn't anything that's going to damage or hurt the customer that's in the costume before you ship it out. And of course, these costs here are once they're done doing all the inspections and the special add-ons and costumes, how much it costs to get to the end customer. All right, so from what we see here, we have supply coming out of Albany, Boston, and Hartford, total of 1,530. Everything has to come through either Charlotte or Richmond, and then after that, be sent out to our 4 in-destination locations. And we see that our actual demand is 1,425. So for this particular production cycle, whatever it is, we're able to make this much, and our demand is this much. So what that means is whenever we model our supply constraints, we're going to have inequalities for that. But for our demand constraints, we will have equations. All right, so our decision variables again, number of outfits or number of costumes. And let's say if we did from, let's say, Albany to Charlotte, that's going to be our route, or how many of these outfits go from factory to finishing. Then, of course, let's say from Charlotte to Dallas, that would be a situation of going from finishing to the end customer. So our goal here is to, of course, minimize the cost. And so if you notice, we have two types of cost here. What's in red is actually describes the cost going from manufacturing to finishing. Okay? In other words, from the factory to Charlotte and or Richmond. So you can see with all of these, either the end destination is Charlotte or the end destination is Richmond. Okay. And then, of course, what's in the green is actually going from finishing to the end customer. And so you can see from there, everything either comes out of Charlotte or it comes out of Richmond. Now the constraints. If you notice here, the Albany supply is 450. And again, we could rewrite this way if you wanted to. We would say the supply has to be 450 or less, but since we're talking about doing it in terms of everything that's negative is pure supply, everything that's positive is pure demand, that's why you see it written like this. And of course, here this 0 is there because you're looking at this as the net flow. So we want to know the flow going in minus the flow going out. Now, of course, we have nothing going into a supply node, so that's why it's 0. And the flow going out, of course, it's all what's coming out of Albany here, going to either Charlotte or Richmond. So that's why here on the left side is going to be negative. Okay. Similarly for Boston and Hartford, these are pure supply nodes, so the zeros are there just to show that nothing's going in. For the net flow for Charlotte, we got everything coming in from Albany, Boston, and Hartford. But once all that's in, then of course all this stuff has to come out and go to Dallas, Louisville, Memphis, and Nashville. Okay. Same thing for Richmond. You got everything coming into Richmond, but after that we have everything going out, going to either Dallas, Louisville, Memphis, or Nashville. And again, for our demand nodes, of course, we're receiving everything going in, but nothing going out of the demand node. Okay? So for Dallas, for instance, we see that we have product coming from Charlotte and product coming from Richmond to Dallas, but nothing's leaving out because, of course, that's where our end customer is. So we don't want to ship it somewhere else. Of course, all these other ones follow suit. Now, of course, if we model that, this is what it would look like. And the main thing that I want to emphasize here is where you see all of these $2,000 placements here. Okay? The reason that they are there is because there are some routes that you do not want to take or that you can't take. For instance, you can't ship straight from Albany to Dallas, right? Because regardless of what you're talking about, whether it's Albany, Boston, or Hartford, all of these have to either go through Charlotte or Richmond for finishing. So, of course, you got Dallas, you you got Memphis, you got Nashville, and you have Louisville here. But all that has to go through either Charlotte or Richmond. There is no direct way to get from Albany to Dallas. There is no direct way to get there. So we use these 2000s here, or you can use any number, but it has to be significantly larger than some of the other prices that we have. But we use those numbers to basically price out those options. Okay? And that is the point of that. So since the Excel solver, when it looks at all this, is going to look at rows at a time, you want to make sure that you have something in place of that. You just don't want to put 0. Because if you put 0, then it's going to say, well, hey, it's free to ship all this stuff there. Of course it's going to take it. So if you put a big number there, it'll price it out and basically ignore that as an option. Okay? And that's also why you see here why you end up having zeros for Albany to Dallas, and Albany to Louisville, and Albany to Memphis, and so on and so forth. Because of course, you can't really, ship in those places anyway. So it should be priced out. Okay. All right. So now we're going to talk about our assignment model. So for our assignment model here, we're basically going to figure out of these 3 workers here, who's going to do whatever project. And so for the project, we have how much it costs for a particular person to work on each of these projects for an hour. And what we want to do here is figure out the cheapest way to make that happen, of course. So one way that we could do this is we could just do it by brute force and say, all right, well, if we let Adams do project 1, and then Brown do project 2, Cooper do project 3, then we could come up with all the different scenarios for this. And if you notice, we have 1, 2, 3, 4, 5, 6 different scenarios, okay? And so how we actually get that is, let's say if we wanted, for project 1, if we wanted Adams to do project 1, then we only have 2 other choices here. We could either let Brown do project 2, and then Cooper do project 3, or we can let Cooper do project 2 and Brown do project 3. Okay? If we let Brown do project 1, then of course you can let Adams do project 2, or you could let Cooper do project 2. Then if you chose Adams doing project 2, then of course Cooper does project 3 here. If you chose Cooper to do project 2, then Adams has to do project 3. And then similarly, if Cooper does project 1, then Adams and Brown can do project 2. And if you choose Adams, then that means Brown has to do the third one. If you choose Brown, it means Adams has to do the third. And so that's how we come up with all these different scenarios. So this is the A, B, C scenario. This is the C, A, C, B scenario. B, A, C scenario. And so on and so forth. So here, since we're trying to basically assign one worker to one project, all that we're dealing with here is ones. Okay? In particular, for Adams, since the workers are going to be peer supply, meaning supplying the work, we're going to look at this as negative, and the project is going to be looked at as positive for the demand. And so the way that we'll label the decision variables is the number of projects here, and of course it's just going to be 1. So our choices here are either going to be 0 or 1, where 0 means that the project is not taken by that person, and 1 means the project is taken by that person. So here if I said Adams 2, then that means that Adams, if this equals to 0, then that means Adams did not take on project 2. But if this is equal to 1, then it means that Adams did take on project 2. So now, of course, if we model everything, we know Adams has a choice of taking project 1, project 2, or project 3. The goal here is going to be -1, meaning that he's going to pick one of those, and that's going to be the supply. Same thing for Brown and Cooper. And then, of course, for the demand, which is what project are you going to do? We know that Adams does project 1, and that would be a 1, the rest of these would be 0. Okay? Or if it's the other way around, let's say if Brown decides to do project 1, then the 1 will be here, and the 1 will be here, and the zeros will be there. And of course, we want to minimize the total cost. So everything that we see here, we just attach the corresponding decision variable to it. So for instance, in this one, this is the number of, I guess the project's going to be assigned to Adams for project 1. So if this actually ends up being a 1 here, then that means Adams got project 1, and we're charging $11 an hour for that. Where these other two would actually be 0 because Adams won't get project 2 and project 3 because he would only do project 1. Thus, we form our objective function solely from this cost chart here. All right, and so once we run everything, we see how by the ones that tells us what is being assigned. So basically, Adams got project 3, Brown got project 2, and Cooper got project 1. Okay? Of course, here's all of our cost. Now, you may be asking, if we did it this way to start off with, why in the world do we even need to put that in Excel? So the answer to that question is this. This is just a small clock repair shop. Let's say if we're dealing with a massive project that we're working on, let's say for an airline. An airline has tens of thousands of workers. And for a particular division, let's say you have 200 people. If you have to assign 200 people to do these various projects, and there's going to be a cost associated with it, you do not want to figure out for how many projects you have times 200 people, what that's going to be. Okay? So that, of course, is going to be a whole lot. By the time you do all this, you're going to wish that you had Excel to do it. So this is just a simple example, but what this is really for is whenever you're dealing with more people, more larger situation. All right, so let's go ahead and talk about the maximal flow model now. So in this example, we have a situation where we're trying to find the best way to get, let's say, trucks or whatnot to travel through the city, okay? And so each of these numbers here actually tell us the amount of cars that can go in a particular direction. Okay? So, for instance, if we're going from node 1 to node 2, then what this means is we got 300 cars that can go that way, but only 100 cars that can go this way. Okay? And of course, if we're going from 1 to 3, this means here 1,000 cars can go that way, but no cars can go this way, which means this is a one-way street. And so when we do this, part of what we want to do is break out when we have a one-way street versus when we have a two-way street, because we need to be able to see everything. Okay. Now, our objective is to maximize the number of cars being able to go from 6 to 1. Okay. So in other words, being able to come from here to here. And the reason why we're wanting to do that is because we're trying to balance this off here. So I'm going to erase here for a second. we're going to try to balance off. And so in balancing off, we know that everything that we see here, regardless of how the flow is, if we want to be able to get stuff to flow as efficient as possible, we're going to need to have some kind of equation to balance everything. And so what we're going to do is come up with a dummy arc. And that dummy arc is going to go from here to here. And we're going to give it like a really large number, like 200, which means essentially 200,000 cars to go from here to here. And by us working on the part that's circled in black to get the flow right, if we have this dummy node here, it kind of closes everything and allows us to be able to balance out what has to go on in between all of these edges and nodes. If we have a large enough capacity in the dummy node to be able to balance everything out. So that's why our objective function here is to maximize the amount of cars that can go from destination 1 to destination 6. And again, really what we're doing here is we really want to know how can you get from 1 to 6, but we're just turning it around. Of course, here we want to know really how you get from here to here, but we're doing it the opposite way by creating a dummy node. And so here, that's pretty much what I've been saying. We want to maximize the amount of cars go from here to here, and we put 1,000 here to represent that we could basically have 1,000,000 cars go through them. And you also see how we've broken out the two-way and the one-way. So if you remember here, we said that we had 300 cars that can go in this direction from node 1 to node 2, but only 100 that can go in this direction. Whereas here, we had 1,000 cars that can go in that direction, but none going back the other way. Okay. And I know, like for here, I'm saying 1,000, but that's because in this problem, if you actually read it in the textbook that it comes from, they're looking at this as in hundreds. So if you take 10 times 100, that's going to be 1,000. Or if you take here, you take 3 times 100, that's going to be 300. So that's why I'm saying that. All right, so here, if we model all of this, we see that this is the amount going into node 1. This is the amount going out of node 1. So I'll go back and show you how we put this together. So let's erase this. Now, we see here, and we're going to do different color. We notice here that we have the X61 going into node 1. And we also see that we have X13 going into node 1. But what's coming out is X12, X14, and X13. Okay? So we got these two going in, where all 3 of these are going out. And that's why you see what you see there. So X61 and X21, oops, yeah, that was wrong. Let me correct that. There should be 2, 1 there, which is going from node 2 to node 1. And of course, here you're going from node 1 to node 2, node 1 to node 4, node 1 to node 3. And that's why you see it. And of course, the net for that is going to be 0, because again, we want everything balanced out so we can see how much is actually going to go through this particular node 6.1. And of course, if we do that to all the other nodes, and this is what we'll end up getting. Now, all these constraints that you see there are what we actually seen from the beginning, which is we know that going from, and I'll just use this as an example, from node 1 to node 3, we know that the maximum amount that I can get going there is going to be 10, or we'll translate that to 1,000. Okay. We also know, let's say going from node 1 to node 4, we know that the maximum amount I can have there is 2, or 200 cars. And so that's what all this is about. Now, of course, once we model everything, of course, you see the 1,000 that's there. And what the 1,000 is going to be there for is basically saying that we really do not have anything going from node 6 to node 1. But we're trying to, quote unquote, put something there that's going to make that unattractive so that it forces everything to balance out on the other side, which is the actual network that we have. And of course, you'll see once we model everything and put it in, that we end up saying from node 1 to node 2, we want to have 200 cars go through there. From node 2 to node 1, we don't want anything. So if we look back here from node 2 to node 1, we don't want anything going from here to there. Okay? Oops, sorry. And of course, for this one, from node 6 to node 1, you notice that one's got 5, so it's got a lot. And from here, from node 3 to node 5, we want sizable amount. Okay. And so thus, everything that's in yellow there is kind of what makes sense as far as what is allowable. Now, if you notice, I do not have anything here from, let's say, node 2 to node 3. And if we go back, we'll actually see that. So this is node 2, and this is node 3. There is no direct connection in between node 2 and node 3. So that's why in my model here, you see I have nothing there. Okay? I only do the yellow cells on where we actually have something that's in, that has a direct connection.